Greetings, everyone. I'm Tim Larson, and today I'm talking about plastic scintillation detectors. So, scintillators are materials that emit photons after absorbing ionizing radiation. They're an example of luminescence, and they can be solids, liquids, or gases. And what's happening with the scintillator is that the material's absorbing the radiation, the X rays or gamma rays or heavy particles, where the photon energy is transmitted via photoelectric effects and Compton scattering or pair production, and the energy is transferred to the charged particles, creating a large number of excited electrons and electron holes during that absorption process. Those charges migrate around the material, and depends on the conduction properties of the material crystal used. But what happens then is that those energized electrons and electron holes, they recombine and they release the luminescent photons. And that's what you can see here. This is a long long exposure digital photo of some various materials after being exposed to cesium 137 gamma radiation source. At the top, labeled as plastic, and it's kind of emitting a violet luminescence. And then next to are some other similar materials. The blue can is a sodium iodide. The green bar is a cesium iodide. And so I think other presentations will be talking about those types of materials, but our presentation is going to be on plastic scintillators. Uh, Plastic fiber scintillators, like you see on the right here, are commonly used in portable equipment. Besides dosimeters, you can see them in telescopes, real-time imaging systems, X-ray imaging systems, and they have some advantages because as a fiber, they have some flexibility and they can be installed and applied in different configurations. So in this configuration, the scintillation material is at the tip of the fiber, and this is what interacts with ionizing radiation that's generating the visible light, luminescent light during the interaction, and that light energy is being directed down the optical fiber, and because of the total internal reflection, it stays within the fiber. So these charts on the left, which are from the Andreo textbook, these are a few examples of scintillation light emission spectra of selected plastic fibers and plastic materials from the list below. The top chart shows the wavelength versus intensity by wavelength of the various plastic formulations. And while this is a selection, there are a wide variety of scintillating fiber plastic formulations, and they will generally emit light in the blue spectrum, although these examples have a couple in the yellow green part of the spectrum too. So, why plastic? The plastic has a high kind of tissue equivalent response. The polymers have a high number of hydrogen and carbon atoms, and when they're used in dosimetry applications, you're seeing fiber materials that have very high tissue equivalents, or they also have high water equivalents. So that makes them very useful for these applications. So let's talk about scintillation dosimetry. Because the scintillators emit light in a very predictable way based on the properties of the material. Each material having its own kind of response rate and emission spectra. That light can be captured and converted into a signal, and an electrical signal that we can record and can be measured. And the signal of the detectors is not a direct measure of dose, as we'll talk about a little bit more. But let's look at this schematic of a typical sort of detector here on the left. On the left side is the scintillator material. It could be a piece of plastic or the fiber tip. And this is where the incident gamma radiation is absorbed, and the energy is transferred within this to charged particles, as we described. And that kinetic energy excites the electrons and it gets dispersed throughout the scintillation material. the scintillator material. And then when they relax, of course, they relax back to stable energy. They release the photons, and those get guided towards the second part of the schematic, which is called the photomultiplier tube, or PMT. And so those photons hit the photocathode at the start of the tube, and that generates an electron being released into the PMT. And the PMT converts, again, the photons into electrons and accelerates the electrons through a high voltage electric field within the PMT. And as they accelerate, they interact with these photodiodes, this chain of multiple diodes, rather. And at each one, it releases more electrons along the chain. And the effect of this is to amplify the signal. The reason the amplification is needed is because the primary signal from the scintillating material is very low. But after it's amplified, the output, which is proportional to the input, like electron, usually by as much as 10 to the power 7, and the output signal is able to be read much more clearly than the input signal after amplification. And the outputs can either be charges counted or measured as a current. Now, again, the output is not the dose, but it's a measure of the accumulated charge that was detected in the material, in the scintillation material. But a dose, you could do a dosage calibration that would be used to convert. If you set your scintillator and test it to a known dose, once you have that conversion factor, you can use the values returned from your scintillator as in real time as a direct conversion to your dose. So these are just some examples of industry devices. I've not personally used any device, but it's easy to find abundance of commercial industry products being offered in the market just to kind of get familiarized with them. This one on the left is called the X-Radon W2, and it's a fiber scintillator, and you can see the fiber mounted here on a liquid ionization chamber, and it connects via a fiber optic cable to this blue laptop size kind of PMT module. And then the signal's processed in yet a third unit here. You'll note here that unlike the schematic above where the scintillator was connected right to the PMT, the fiber here is separated from the PMT by this long optical fiber. And that actually helps by removing this PMT module from the field of radiation. So without exposure radiation, radiation could potentially damage PMTs, or it could create noise in your signal. And this onto the right is just another example of commercial products that I found online, just to kind of familiarize myself with them. Just a few notes about additional signal concerns. So when you're reading signal from plastic scintillator detectors, there's known to be noise created by an effect of radiation-induced light called Cherenkov noise. The Cherenkov radiation is produced when charged particles pass through a medium that it's greater than the speed of light in the medium. And this creates a blue wavelength light. And the effect of that is to add that noise to your output signal. So this chart on the right shows the spectrum of the typical Cherenkov noise, and with the scintillation signal, combined effect of that is this combined signal here. So most, I think, products will either need correction or will already be correcting for a Cherenkov signal, and there's a few methods to do that. There's also potential for noise from dark current in the photodetector, or radiation exposure to the photodetector, as we described in the setup, keeping your PMT away from the field of radiation. And also, clear plastic has a tendency to have a yellowing effect due to age and due to exposure radiation. And it will actually filter your signal and your spectrum that is being recorded. So devices need to be regularly recalibrated due to plastic yellowing. So, in summary, we talked about scintillator materials and processes. We did an overview of scintillation properties of plastics and fibers. Also, the dosimetry principles using plastic scintillators, and with an example of a typical device setup, and talked about some of the concerns reading the data, the signal that comes out of the detectors. Um, Thank you guys so much for listening to my presentation.